Mm-hmm.
Hello everyone, I hope you're doing well. In this video, we are going to solve problem 15 from chapter 12 of Material Science and Engineering by Callister. The chapter name is actually maybe ceramic structures, crystal structures, and it is related to theoretical density of ceramics. And here we'll be calculating the theoretical density of diamond. Let's see the problem statement and we'll dive directly into the solution. The statement says that compute the theoretical density of diamond given that the carbon-carbon distance and the bond angle are 0.154 nanometer and 109.5 degree. So 0.15 nanometer is actually the carbon-carbon distance and 109.5 degree is actually the bond angle between the carbon-carbon bonding respectively. Okay, how does this value compare with the measured density? So what you have to do basically in this video, in this problem, is to calculate the theoretical density or the volume density of diamond using these two parameters that are given. They'll help us, and after finding out this theoretical density of diamond, we'll compare it with the experimentally determined density, okay, that we call as measured density in here. So the experimental value for the density of diamond is actually 3.53 grams per centimeter cube. All right, this is the experimental value. This is the experimentally determined density, and we'll compare it with the theoretical density at the end of this video, and we'll see what we can do about it. Let's quickly get started with the solution. First of all, we'll write down the formula that we'll be using to calculate the density. We know that the density is given by now keep that in mind that diamond is made up of similar carbon atoms only. There is no different atoms. It's made up of similar kind of atom, which is carbon. Hence we have rho equals number of carbon atoms per unit cell, okay, number of atoms per unit cell as usual, multiplied by the atomic mass of carbon atom or whatever atom you are considering. Since we are considering diamond, so I wrote carbon in here. You can write C to show that it's carbon, and divided by Avogadro's number times the volume of the unit cell. So that is the formula that we'll be using, and let me call it as 1. And this formula is general. Whatever kind of structure is given to you, if it is made up of similar kind of atoms, you can use this formula. If there are different atoms, you can simply add up the atomic masses, A1 plus A2 plus A3. Rest of everything is same. Even in case of ionic crystals, you'll be using the similar formula, and depending upon the type of atoms present, you have to add up all of the atomic masses. And obviously, if it's ionic crystals or ionic compounds, then you have to consider the radius of ions instead of radius of atoms. There is a difference when you are considering the ionic crystals, and only one difference is that the radius of ion is considered ionic crystals, but not in covalent crystals, because in covalent compounds, diamond is a covalent compound, and in covalent compounds we have neutral atoms. All right, and yes, we have this situation right now, and we'll be using this formula. Now let us see what these values are equals to. First of all, Na is Avogadro's number. Let me write it right away because that's the easiest one. Then N prime, okay, atomic mass of carbon. Atomic mass of carbon is 12 grams per mole. Grams per mole. Then we have N prime. N prime is actually net number of atoms, carbon atoms here. Carbon atoms inside unit cell, single unit cell. So diamond has that structure that we have 8 carbon atoms at each of the corner of the unit cell. Cubic, it has a cubic structure, okay, and 8 carbon atoms at each of the corner of the unit cell, and each of them is contributing 1 by 8 to a single unit cell. Plus we have carbon atoms at face centered point of each of the faces of the unit cell, and there are 6 phases, so 6 carbon atom at the face centered point, and they are contributing half to each unit cell, so it's 6 into 1 over 2. Then we have 4 carbon atoms at the tetrahedral voids inside the unit cell. Like there are some voids, some empty spaces inside the unit cell, and they are called voids because they are, empty spaces, and carbon atoms can occupy those positions, and they are called the tetrahedral position because they are located at 1 over 4th position reference to a specific corner. So we'll be considering it, but there are 4 of them, and they are completely inside the unit cell. They are not shared with any other unit cell, so they are completely inside, and there are 4 of them, so it's 4. Let's find out the net number of atoms. 8, it cancels, and it's 1 plus 2 into 3, so it's 3 plus 4. And it is 1 plus 3 plus 4, that is equals to 8. And net number of atoms per unit cell of a diamond-like structure is 8. All the structures that resembles the diamond structure has 8 number of atoms per unit cell. You can use it because they are used for example, silica as well, to show their geometry and all that stuff. So that really helps when they tell you that a certain structure resembles a different structure that you are really comfortable to use. So if you are comfortable with diamonds, you can use it as a reference to calculate the other structures as well. So that is the net number of atoms per unit cell. And diamond actually has FCC structure, but there are 4 atoms inside its body as well, and they are located at the tetrahedral, as I told you people, 1 over 4 position, and there are 4 of them. So it's a mixed structure, but it is cubic overall. All of these sides lengths are equal to each other. It has a lattice parameter A, you can see, and it's same in the 3 dimensions. We need to calculate the volume. Volume is given by, volume of diamond is diamond with lattice parameter A. If A is the lattice parameter, then the volume is given by A cube. We need to calculate A because we don't have it, and that is the formula V equals A cube. Let me call it as equation number 2. Let's calculate A first, and then we can calculate the volume, and we'll put all of these values into this expression to calculate the density of diamond. Now we were given with carbon-carbon bond length. Carbon-carbon bond length was equals to 0.154 nanometer, and you can write it as 0.154 multiplied 10 to the power minus 7 centimeter. I hope you got it because I want the results in grams per centimeter cube. That is why I'll be taking the lengths in centimeter. It's really easy to convert it. Like if you have 0.154 nano is 10 to the power minus 9 meter, you can write it as 0.154 multiplied 10 to the power minus 7 multiplied 10 to the power minus 2 meter. Minus 7 minus 2 is minus 9. So you can do that, and it is 10 to the power minus 2 is actually centi, so we can write centi in place of it. So it's like that. It's really handy if you do it like that. All of the density calculation will require you to use the lengths and radiuses and everything in centimeter units, and the answer you will be getting will be in grams per centimeter cube automatically. So it's a good thing to do. And this is the carbon-carbon bond length, and it's not equals to A, okay, it's different. Then we have the carbon-carbon bond angle, okay, the angle between the two bonds, that is 109.5 degree. Let's see how we can utilize this information and calculate the lattice parameter from the figure, because you have to see the figure in order to understand it. Let me take you to the figure. This is the structure of diamond. We can see here this is one of the corner atom, and I'll be considering only those that will help us to calculate the lattice parameter. I'll be not considering all of the atoms. So this is the tetrahedral void location, and this is the carbon atom at this tetrahedral position, and then we have this carbon atom, and these dashed lines are actually representing the bond. Okay, dashed lines are representing the carbon atoms which are bonded to each other, and we can see not all of the atoms have this dashed line with each other, which shows that not all of the carbon atom are directly bonding with each other. Only few of them are bonding with each other. So we will be considering only those carbon atoms to calculate the lattice parameter which are bonding with each other, because we have the carbon-carbon bond length and we want to use it. So I'll be using these 3 carbon atoms that I dotted, and we can form a figure out of it to use. And we have this this triangle, like one like that, they joining together, and this, okay. And I'll be using the law of cosines in order to find out relationship between the lattice parameter A and the bond length. Okay, so what this length is actually. Okay, let me first talk about this length. We can see that these two carbon atoms are bonded to each other, hence their distance with each other is actually the carbon carbon bond length, and let me call the carbon carbon bond length as B. Okay, this distance is B. We know this distance, that's good. Then we have another distance, that is this. These two carbon atoms are also bonded with each other, you can see, so their distance with each other is also B. All right, and the only length that we don't know in here is this length. All right, and we can calculate this length in terms of lattice parameter A, because we have the cubic structure and we can easily find out this diagonal length. So let me first find out this diagonal length and then we can calculate the lattice parameter. Let's calculate this unknown length, which I'll be calling as C. Okay, and then we can calculate the lattice parameter out of the information that we are given. Okay, I'll be using the law of cosines. Okay, this is the length that we don't know, and other than that, one more thing that I want to mention before I calculate this unknown length, it is that you can see that these two atoms are bonded with each other, and these two atoms are also bonding with each other, and bond angle is actually the angle between two consecutive bonds. So we can have this angle, which is, let's say, alpha, and this is actually 109.5 degree. Okay, angle between two bonds is actually 109.5 degree. Like we have these two bonds and its angle is 109.5, this angle is also 109.5, and so on. All right, so let's calculate this diagonal length. That is really easy for us. We can see that we want to calculate this length, and it's this atom, this one atom, that center atom is right at the center of the whole unit cell. So let us calculate this total length, which is this diagonal length. We can cut it into half at the end. So, and we have this length, which is A, and this length, which is A as well. All right, these are the lattice directions and these lengths are A. So we can find out this unknown length from the Pythagoras theorem. This whole length is D. We can use Pythagoras theorem really easily to find out this D length, which is the hypotenuse, and D square will be equals to A square plus A square. All right, and hence D square is actually equals to 2A square, and D would be equals to under root 2A. All right, so this whole length, this total length, full length is under root 2A, and since we want only half of it, and because that is the part of a triangle, so I'll be dividing it into half. Let me do that. Let's divide this length into half. D by 2 is actually C that we wanted, and C is equals to under root 2 by 2A. All right, this is the C length, and yes, we have got it. It's under root 2 by 2A, and I hope you can see that we have successfully calculated this length, and this length is actually B. This length is also B, and this length is under root 2 by 2A, and we know the angle. This is the angle 109.5 degree that I'm calling it as alpha. Let's use the law of cosines, and law of cosines will help us to find out relationship between these parameters with each other. Let's draw the figure that you are supposed to draw on paper as well. Like when you are solving it in exam, you have to draw this figure because you can't remember these values. You have to show that you have that expertise to calculate it. So first of all, we'll draw the cube. This is the cube, and then you are supposed to draw only those atoms that matters. So this is the corner atom, one of the corner atom, and this is carbon atom, and another atom is this body centered atom, which is located at the center of this ground plane. It is right at the center. This is the face centered atom, and then we have the third atom, which is present at the tetrahedral void. Okay, this is the atom which is present at the tetrahedral void, and as we have seen that they were bonding with each other, and these two were also bonding with each other, but they are not bonding with each other. All right, keep that in mind. And we have this angle between these two bonds, which was alpha. let me write it as alpha, and alpha was 109.5 degree. That is the bond angle that is given in the paper, oh sorry, exam question. And this is carbon, and this is carbon as well. This length V is the bond length, and we can let it to be B. This is the bond length as well, because they are bonding with each other, hence the length or the distance between two bonded carbon is B, which is the 0.154 nanometer. Okay, that was given. So that is why these two lengths are B. And this length that we calculated right now is under root 2 by 2 A, and you can even write it as 1 over under root 2 into A. You can do it on calculator. It's just like we have 2 to the power 1 by 2 and 2 to the power 1. So if you take it above, subtract the powers, and you'll get this thing. You can use this and this as well. It's totally up to you. And yeah, this is the kind of situation that we have in here, and you are supposed to draw it on exam while solving it. I'm telling you again and again, because don't be lazy. You'll lose your marks. It will add good detail to your answer. So that is the situation right here. Let's write down that what is B. B is the bond length, carbon-carbon bond length, that is equal to 0.154 multiplied 10 to the power minus 7 centimeter. Then we have alpha, which is the bond angle, and that is equals to 109.5 degree. And what else? It's this C length, which is 1 over under root 2A. All right, and next what we need to do is to use the law of cosines, as I told you people earlier. And you can't use Pythagoras theorem here. Keep that in mind. Be alarmed, because Pythagoras theorem could only be used in those triangles which have at least one angle as 90 degree. It's only useful for the right angle triangles. You can't use Pythagoras theorem in other triangles which doesn't have 90 degree angle in them. So you can see none of the angle is 90 degree, and you have to use other laws for that, and it's law of cosines or law of sines. I'm using law of cosines because that is what would be helpful in our case. So using law of cosines, in law of cosines, what happens is that you take one of the side. I'm taking this side because opposite to this side we know the angle. You should choose only the side opposite to which the angle is known. So since we know this opposite angle, which is alpha, so we'll take this side, and it is C. So C square, square of this side, which is B square, plus square of this side, which is again B square, then minus 2 into this length, which is B, dot this length, which is also B, times cos of angle between them, which is alpha. So this is the law of cosines. C square equals B square plus B square is 2B square minus 2BB is B square cos alpha. We can put the value of C in here. C is 1 over under root 2A whole square. 2B square, we can take 2B square common, so it's 1 minus cos alpha. Here it's A square divided by under root 2 whole square. 2 and under root cancel, it's 2 only, and we can take 2 to the other side, so it's 2B square, 1 minus cos alpha. So A square is equals to 4B square, 1 minus cos alpha. Taking under root on both sides, so A is equals to 2B, 1 minus cos alpha under root. Under root of 4B square is 2B. That is why I just wrote it directly, to save some time. Alright, so this is the lattice parameter A. Now let's calculate the lattice parameter by putting the values in here, and then we'll calculate the volume, and then we'll put the values right back into the equation number 1. It's almost done. The difficult part was to determine the lattice parameter, and we did that. Let's put the value in here. So it's 2 into B, which is 0.154 multiplied 10 to the power minus 7 under root 1 minus cos of 109.5. So let's calculate what does this equals to. This is the value that we got. So what I did is I just calculated this thing first, then I took under root of it, and then I multiplied with these quantities. So the result that we got, this is the result, 3.557 multiplied 10 to the power minus 8, and it's in centimeter because bone length that we added was in centimeters, so the result is in centimeter, and hence volume is actually given by V equals A cube. So V equals 3.557 multiplied 10 to the power minus 8 whole cube. So taking the cube of it is what you got as volume, and it is 4.5 multiplied by 10 to the power minus 23 centimeter cube. That is the volume. Now let's put all of these values, putting values in 1 to calculate the density, and hence density is equals to n prime carbon atomic mass, Avogadro's number times the volume, and n prime is 8 multiplied by atomic mass, which is 12, divided by Avogadro's number, which is 6.023 multiplied 10 to the power 23, volume, which is 4.5 multiplied 10 to the power minus 23. And let's do all of this calculation and see what the result is. Firstly, we can see these two powers cancel out. It's minus 23 is plus 23, so we have this thing. You can see here it is 3.54 grams per centimeter cube. This is the density of diamond that we got theoretically, and we had rho measured or experimentally, you can say, to be equals to 3.53 grams per centimeter cube. 3.53 grams per centimeter cube. Let's find out the percentage error between the theoretical result. This is theoretical, you can write theoretical, and this is the experimentally measured. Let's see what is the percentage error. The percentage error is given by percentage error between the measured value and the theoretical value. So you will take the greater value, you will subtract it with the smaller value, and you will divide it with the standard value. The standard value is actually the experimentally determined, because that is the accurate one. So we'll divide it with the experimental value. You always divide it with the standard value, so we'll multiply it with 100 to get the percentage. You can see it's 0.283%, and you can see the error is really small, less than 1% between the measured density of diamond and the theoretical density. In this way, the question is done. There are other problems as well in which the lattice parameter is not directly given. So you are given with bond angles and the length between the two bonds. So you are supposed to find out the positions where the two atoms are bonding with each other, and using a really clever position where these calculations could be made. Just choose that position and find out the parameter, which is actually the lattice parameter, out of it really easily, as we did for the diamond. Okay, and yeah, this is it for this video. I hope you got it. Like, share and subscribe, and keep watching. I'll be uploading more of these.